Jnanam Paramam Dhyayam. Knowledge is supreme.
In the last lecture, we started by assuming that the external resistance to mass transport and the internal resistance to mass transport are actually comparable. And we want to understand how to quantify this particular situation where both the resistances are comparable. We also observed that at steady state, the rate of transport of the species from the bulk to the surface should be equal to the rate of the reaction in the surface area inside the catalyst pellet and also on the external surface of the catalyst pellet. And this is because the reaction can happen both at the external surface and also in the internal surface where the active material is actually coated. Now, we also compared what is the typical surface area which is available for the reaction inside the catalyst pellet, and also compared that with the total area which is available in the exterior of the catalyst pellet. And let us look at that numbers again. So, we said that the total area for the reaction is essentially equal to the internal area plus the external area, and the internal area is essentially given by AC into delta V, and the internal area is essentially given by SA, which is the active surface area per gram of catalyst multiplied by the bulk density into delta V, and the external surface area is given by AC into delta V. We looked at the numbers for these two for typical catalyst, and we saw that AC is typically of the order of magnitude of 1400 meter square per meter cube of the catalyst, meter cube of the reactor volume, and SA rho B is of the order of magnitude of 84 into 10 to the power of 6 meter square per meter cube of the reactor volume. So, from here we can clearly see that SA rho B, which is the internal surface area which is available per unit volume of the reactor, is significantly higher than the external surface area of the catalyst pellet that is available for reaction. So, clearly this is typically larger, much larger than the external surface area. Now, this we specifically saw for the silica alumina catalyst, and in fact this is true for most of the catalyst pellets. Most of the pellets that are actually being used in the industry these days. So, how do we incorporate that in the balance? So, let us see what the balance is in the first place. So, the balance was that we said that the rate of transport of species from bulk to catalyst surface, which is equal to the flux with which the species comes from the bulk to the catalyst surface, that multiplied by the area per unit volume of the reactor into delta V, and we said that that should be equal to the net rate of reaction occurring within and on the pellet. We also observed that this should be equal to minus RA double prime, which is the rate defined per unit area of the surface which is available for reaction, and that multiplied by the total area. So, that multiplied by the A total, which is equal to minus RA double prime into SA into rho B, which is the area corresponding to the available surface inside the catalyst pellet, plus the external surface area into delta V, which is the volume of the reactor. So, now we can cancel out the volume terms and we can actually reduce this equation, and so WAR into AC into delta V is equal to minus RA double prime into AC plus SA rho B into delta V, and we can cancel out the volume term here, and so from here it reduces to into AC equal to SA into rho B. Now we also observed that SA into rho B is typically much larger than AC. So if we ignore this small term inside the area total, we can further reduce this equation to WAR into AC is equal to minus RA double prime into SA into rho B. Now what is the flux with which the species actually diffuses from the bulk to the surface? We already characterized that when we looked at the external resistance to mass transport part, when we quantified the external resistance to mass transport. So what is the flux? The flux WAR is essentially equal to some whatever mass transport coefficient that multiplied by CAB minus CAS, where CAB is the concentration of the species in bulk. So this is the bulk concentration, and CAS is essentially the concentration of the species at the surface, where the diffusion is actually happening from bulk to the surface of the catalyst pellet. So we can plug that into the balance, and what do we get when we plug that in? So that will be Kc into CAB minus CAS, that multiplied by AC is essentially equal to minus RA double prime into SA into rho B. So this is the bulk density. So now we know this expression. What do we do next? We said that we want to assume a first order reaction. So we can now use the property of first order reaction to actually find out what is this RA double prime. Now how do we substitute that here? Now suppose if we also said that the internal diffusional limitations or internal resistance to mass transport is comparable to external resistance to mass transport, which immediately suggests that the internal resistance to mass transport is not negligible. So if internal resistance to mass transport is not negligible, we saw in the internal diffusional limitations case, we saw that the overall rate at which the reaction happens can be related to the rate at which the reaction happens if the species is actually at the surface concentration, or we can relate it to the intrinsic kinetics by using the internal effectiveness factor. How do we do that? So we can now say that the RA double prime is essentially equal to the internal effectiveness factor eta multiplied by RA at the surface conditions, RAS at the surface conditions. Now we said that we want to do this for a first order reaction. What happens when we actually plug in the kinetics of a first order reaction? For a first order reaction, what is the intrinsic kinetics? We know the kinetic expression for the intrinsic kinetics, which is essentially RAS double prime is essentially equal to some rate constant K1 corresponding to the first order reaction multiplied by the concentration of the species, which is basically that it is actually at the surface conditions. So plugging that into the balance, we will see that the minus RA double prime is equal to eta into K1 into CAS, and plugging this into the balance, we will see that Kc into CAB minus CAS, which is the rate at which the transport happens multiplied by the external surface area per unit volume of the catalyst, and that should be equal to eta K1 CAS SA into rho B. So this is the balance which relates the external mass transport rate to the total rate at which the reaction happens. So, what are the measurable quantities? So, the measurable quantities are essentially the bulk concentration. We will not be able to measure what is the concentration of the species at the catalyst surface. So, therefore, we can use the balance to eliminate the concentration of the species at the catalyst surface. So, we essentially want to eliminate this quantity, we want to eliminate the concentration of the species at the surface, and how do we do that? We can use this expression, we can do a little algebra. So, the algebra suggests that Kc into Cab into Ac minus Kc Cas into Ac, that should be equal to eta K1 Cas into Sa into rho b. So, now from this we can find out that Cas is essentially equal to Kc into Cab multiplied by Ac divided by eta K1 double prime Sa rho b plus Kc into Ac. So, the concentration of the species at the surface is essentially given by this expression here. Now, how do we further use this expression? We know what is the overall rate at which the reaction happens in terms of the effectiveness factor and the rate at the surface conditions. We can substitute this into that expression. So, from here minus Ra double prime is essentially equal to eta into minus Ra S double prime, and that should be equal to eta into K1 double prime into Cas, and we know what is the expression for Cas. We can substitute that here, eta K1 double prime Kc Ac Cab divided by Kc Ac plus eta K1 double prime Sa into rho b. So, what we have found is the overall rate at which the reaction happens per unit area of the catalyst in terms of the bulk concentration of the species, which is actually a measurable quantity, and all the recall that if you look at this expression, all the other quantities are actually a known quantity if the effectiveness factor of the catalyst is known. K1 double prime is the intrinsic kinetics, Kc is the mass transport coefficient, Ac is the external surface area per unit volume of the catalyst, and Sa rho b is the they are the surface area, internal surface area per gram of the catalyst, and rho b is the bulk density of the bend. So, once we know these quantities, we can actually find out what is the overall rate at which the reaction happens in terms of the bulk concentration, which is typically a measurable quantity or an observable quantity which can be measured when the reactor is actually run. Now, earlier we defined a quantity called the internal effectiveness factor when the internal resistance to mass transport is actually present. Now, in this case, the resistance to external mass transport and the internal mass transport actually are comparable. So, let us first look at what is the definition of the effectiveness factor when only the internal resistance to mass transport is present, and we can extend that to the situation where the external and the internal resistance to mass transport are actually comparable. So, the effectiveness factor when only the internal resistance to mass transport is present is essentially given by the actual overall rate of reaction divided by the rate if the catalyst is at surface conditions, that is concentration Cas and the temperature Ts. Now, in a similar fashion, this is true only for this definition is when only internal resistance to mass transport is present. And the external resistance is to mass transport is negligible. Now we can, because bulk concentration is an observable property, we can now introduce a new definition where the effectiveness factor will now be defined based on the bulk concentration or bulk conditions, which is what is called as the overall effectiveness factor. So, let us see how to define that now. So, the overall effectiveness factor, typically the symbol that is used is this capital omega, which is the overall effectiveness factor. And the definition for this is, it is the ratio of actual rate of reaction divided by rate if entire surface is at bulk conditions, that is CAB and the temperature in bulk. Note that we said it should be the entire surface, which is the external and the internal surface of the catalyst pellet where the reaction is actually happening. So, the definition of overall effectiveness factor is essentially based on the observable properties, which is the bulk concentration and the temperature of the bulk fluid stream, when the external resistance and the internal resistance for mass transport are actually comparable. Let us see how to find this for a first order reaction. So, we want to now do it for a So, the balance that we wrote earlier and found out what is the overall rate at which the reaction happens, that rate is essentially given by is equal to eta into the intrinsic kinetics rate constant divided by Kc into Ac plus eta K1 double prime SA into rho b. Now, we can rewrite this in a slightly different manner. We can rewrite this as, if I pull out K1 double prime into CAB outside and I divide the expression in the numerator and the denominator with Kc AC. So, this can be rewritten as eta divided by 1 plus eta K1 double prime SA rho b divided by Kc into AC. So, all I have done is I have essentially pulled this two term outside, pulled these two terms here outside, and then we can divide the numerator and the denominator with this Kc AC term, divide the numerator and denominator with Kc AC, we will get this expression. What is there on this, what does these two terms correspond to? This is essentially the intrinsic rate. If I now define a rate based on bulk conditions, and because it is a first order reaction, so this is nothing but Ra based on the bulk conditions, which is nothing, which is basically the intrinsic rate constant multiplied by the concentration of the species in the bulk conditions. So, from here I can now write minus Ra double prime divided by minus Rab double prime is essentially equal to minus Ra double prime divided by K1 double prime into CAB for a first order reaction, and that is equal to eta divided by 1 plus eta K1 double prime into SA into rho b divided by Kc into AC. So, what we saw here, what we see here in the right hand side is what is called as the overall effectiveness factor. Recall the definition of the overall effectiveness factor. It is the actual rate at which the reaction happens divided by the rate if the entire surface of all the catalyst pellet and inside the pores all the surface is at the bulk condition. And now if you stare at this expression on the left hand side, what we essentially have is exactly that ratio. So, what we have on the right hand side of this expression is essentially the overall effectiveness factor. So, let us write down the overall effectiveness factor. So, the overall effectiveness factor omega is essentially given by eta divided by 1 plus eta k1 double prime SA rho b divided by Kc into AC. So, this overall effectiveness factor now accounts for the internal diffusional resistances. It also accounts for the external resistance for mass transport. How do we see that in the expression? We can now stare the expression here. Eta essentially corresponds to the resistance of mass transport inside the catalyst pellet compared to that if the reaction is happening at the surface conditions. So, that takes care of the resistance to mass transport inside the catalyst pellet. And if I now look at the denominator here, the Kc/Ac essentially quantifies the resistance to mass transport outside the catalyst pellet, that is resistance offered for transport of species from the bulk to the surface of the catalyst pellet. What is 1 by Kc/Ac essentially tells me what quantifies the resistance of the external resistance for mass transport outside the catalyst pellet. So, therefore, the overall effectiveness factor for a first order reaction, this is for a first order reaction, it essentially accounts for the external resistance to mass transport, it accounts for internal resistance to mass transport, and of course, it also has the surface reaction terms. Note that the intrinsic rate constant is actually present in the denominator. So, all three processes which are actually occurring or which may be controlling the overall rate at which the reaction happens, all these three are actually simultaneously captured in this important quantity called the overall effectiveness factor. Now, how is the overall effectiveness factor for the definition of rate at different conditions? Let us see how to look at that. So, how is the rate, how is the overall effectiveness factor related to the other definitions of rates? Let us see. How are they related? We know that by definition of the overall effectiveness factor, minus Ra double prime is essentially equal to the overall effectiveness factor that multiplied by the rate as though if it was bulk conditions at every location or entire surface in the reactor. This is the rate if entire surface is at bulk conditions. But we also know that the internal mass transport resistance is actually finite, and if eta is the internal effectiveness factor, we can also define the overall rate in terms of the rate of the species under the surface conditions. How do we do that? So, this is essentially equal to eta into the rate at the surface conditions. So, this is the at surface conditions. Now, we know that the actual rate at which the reaction happens is actually rate per surface area which is available for reaction multiplied by the surface area per unit volume, which tells me what is the rate per unit volume of the reactor. So, let us use the definition and see how to relate the overall rate of the reactor. So, the actual actual overall rate or total rate is essentially given by minus Ra, which is equal to minus Ra double prime into Sa into rho b, which is the bulk density. Note that the external area of the catalyst is actually very small compared to the internal area which is available for reaction, but in principle one could also consider that area which is available for the reaction, but typically it is a very small contribution. So, therefore, the overall rate, actual rate can be related to the rate per unit area multiplied by Sa into rho b, which is essentially equal to minus Rab double prime into Sa into rho b into the overall effectiveness factor, and that is equal to K1 double prime Cab Sa rho b into omega. Now, what is this term here? What is this term been? This is nothing but the overall actual rate at which the reaction happens if the conditions of the entire surface is actually at the bulk condition. So, from here clearly we can deduce that omega is also equal to minus Ra by minus Rb. So, what does it immediately suggest is that this is also should be equal to minus Ra prime by minus Rb prime minus Rab prime, and that is also equal to minus Ra double prime by minus Rab double prime, where this is the rate defined based on surface area, this is the rate defined based on the weight of the catalyst. So, this is minus Rab, which is the rate defined based on the weight of the catalyst. So, therefore, the overall effectiveness factor is uniformly applicable whether the rate is available as per volume of the reactor, or it is available as the per unit weight of the catalyst, or it is available as the per unit surface area of the catalyst. So, to summarize, what we have seen is that we have defined a quantity called overall effectiveness factor for a first order reaction, which essentially simultaneously captures the resistance which is available for, or resistance offered for mass transport outside the catalyst for transport of the species from bulk to the surface of the catalyst pellet, and also the resistance offered for transport of species from the surface of the pellet to the inside of the catalyst, where the actual reaction happens in the pores of the catalyst, in which location the catalyst material is actually impregnated. So, the overall effectiveness factor, which accounts simultaneously for all the resistances, is actually widely used for these kind of systems to quantify the rate at which the reaction happens and what is the observed rate, and to use and to correlate that with the observable, which is basically the bulk concentration and bulk temperature. Starting from the next lecture, we will start looking at how to diagnose whether the resistances are actually present in an observed system if the data of the overall rate at which the reaction happens actually is measured. So, can we identify if the internal diffusional limitations or the external mass transport resistances are actually present in the system that is actually being considered. Thank you.